Okay, so part two. I was trying to get the whole lot into one video, so it stretched out right to 16 minutes. Part two won't be quite so long. So just to recap, what are we doing? We're doing calculus, which is the mathematics of change. And change is either constant or it's non-constant. Constant, it's trivial, it's a straight line. It's gradients of straight lines, rise over run. Where change is non-constant, we've got this. We've got variable change, so we can either calculate the change between 2 points join those 2 points with a secant, a chord, a line, and find the average rate of change just by using rise over run. Also fairly trivial. Important point, really key point, when we want to examine the instantaneous rate of change at a point. What's happening at A? Then the definition of that instantaneous rate of change is the definition, or the calculation of that instantaneous rate of change is the calculation of the tangent, the gradient of the tangent at that point A. Repeat, the instantaneous rate of change at a point is equal to the gradient of the tangent to the curve at that point. So illustrated here, point A, purple tangent, so the gradient of that purple tangent is equal to the instantaneous rate of change at A. That's what calculus is about in a nutshell. Right, so what's the instantaneous rate of this is now the question. So the gradient of the tangent to the curve at A is the answer. So then we went about trying to find what the gradient of this purple line is, and so we went with, well, let's go with an estimation. Okay, let's measure between 3 and 4. Again, all right, it's an average rate of change, but it's a start, and that was 7. Then we said, right, well, let's get in closer. Let's get in and have a look at the secant between 3 and 3.01. This tiny little stumpy line here. So what's the average rate of change there? Well, it was 6.01. So that's pretty good. Then we got serious. And we said, no, let's call this H, rather than we could just keep on going forever and ever and ever with these .001s. Let's call this H, and let's have a look at this this rate of change, this gradient between the points 3 for x and 3 plus h for x. And so if we're on y equals x squared, then this is our y coordinate there, and then at 3 plus h, and we subtract 9, and so we do this. And we did that, and we got 6 plus h. So then we said, right, well, let's make h 0. Let's look at the value of 6 plus h as this expression tends to 0. And obviously, as the smaller we make h, the closer this gets to 6. And so that's known as the limiting value. 6 is the limiting value of this expression as we take h closer and closer to 0. So this limiting concept, really important in calculus. Because if we have a look at this fraction here, and we know just from looking at this is that what we're doing is we're measuring the gradient of a line. So that takes rise over run. Now, if we can't make the run 0, it's not defined at that point. So we can't just sub 0 in here. We have to do some stuff first. So what we've got to do is we've got to get it down so that we can cancel the h in the denominator, and so we're left with this expression here. And once we've got this, we can make h equal to 0. But what we're doing, we're not saying this is the value of this expression at h equals 0. We're saying this is the limiting value as h tends to 0. Really important concept. Okay, so that's where we're up to. At this stage, we're getting pretty close, but we're just still looking at y equals x squared. That's a specific curve, isn't it? So the last step for us really in this differentiation from first principles process is to go, righto, let's look at a general curve, y equals f of x. Okay, between the point, let's take the point x. Let's take the point, so that's x, and that'll have y coordinate f of x. Okay, because that's, well, whatever we put in for x is the function value of x. Let's go to another point, and we're gonna do the same thing. We're going to go h to the right, and if we do that, we're at x plus h, and the function value at x plus h is f of x plus h. So what we've got is a secant. Here, let's join these 2 points. Right, we've got a secant there, and the gradient of that secant is equal to f of x plus h minus f of x, and that's all over h. So what we get is, so that's the gradient of this secant here, and it's kept nice and general with this just f of x. So we've got all this stuff. But what we're going to do in order to find out what the instantaneous rate of change at x is we're going to take the limiting value of this. So the instantaneous rate of change at the point x, f of x, is, and this is sort of the punchline, it's the limiting value as h tends to 0 of this expression, which is just rise over run. It's just this here. There's your run, there's your rise. This here, this distance here is f of x plus h minus f of x. Right, that's that distance there from there to there. And this distance here is h from there to there. So that over that is just rise over run. It's the gradient of this blue line. And as this blue line shrinks, and as we take h, as h gets closer and closer to 0, we go further, like closer along this curve in here to the magical gradient of the tangent at x, which is defined as the instantaneous rate of change of the curve at x. And hence we have our derivative process by first principles. So now let's do the example. So therefore, let's do an example. Find the derivative of, let's say, f of x equals, let's just use the example in the textbook so you've got something else to refer back to. I think it's x squared plus 1. Find the derivative of f of x equals x squared plus 1 by or using first principles. Now I'll explain, we'll get to a shortcut method later, but first principles means use this limiting process. Okay, the derivative, that's what we do when we apply this limit, when we find this gradient and apply this limit, we've found the derivative of the function. It's also called the gradient function. It finds you that rate of change at a point. It finds you the gradient of the curve, the rate of change, gradient of the curve, instantaneously at a point where we've got constant change, where we've got a variable rate of change. Okay, so that's what the derivative means. And the derivative of f of x is f dash x. So therefore, f dash x will equal the limit. So this is, it's like a new language. This means f dash x is, the derivative of fx is f dash x, that little dash there. See the dash? This guy here. Right, that's the derivative of fx, also known as, aka, the gradient function. So called because it delivers the gradient, believe it or not, at any point. It's a function that delivers a gradient at any point. Let's go and find that function for x squared plus 1. You know what this is. X squared plus 1, it's a little parabola, isn't it? Does this, it's vertically translated up 1, that guy there. So the limit as h tends to 0 of f of x plus h minus f of x over h. Now, if f of x is x squared plus 1, what's f of x plus h? Alright, so that we need to put that in firstly. F of x, so x plus h squared. This is a bit of a pain to write all this stuff out. X plus h squared plus 1. Now minus this function, x squared plus 1, over h. Here we go again. There's lots of algebra to do here. I've got to expand this out, x squared plus 2xh. If you can do this, You can pause the video and do this yourselves and then come back and check. Just expand the brackets there. Alright, what happens with these, if we do them correctly, is that we get lots of simplifications. Alright, and it all comes down beautifully in the end. So limit, as h tends to 0, what happens here? X squareds cancel. So you put a little line through those. X squared's gone. 1 minus 1 gone. So we're left with 2xh, here we go, 2xh plus h squared over h. Okay, so what I was saying before, we can't put h equals 0 in here yet, because I'd divide by 0. I can't do that, but I can, and always I'm going to have this situation, I can lose my h's there, so I need to write this limit out one more time. I've got 2x plus h in there. Right, my last step is to then apply this limit. As h tends to 0, this tends to 2x. So what that means is, therefore, f dash x equals 2x. That's my gradient function. So therefore, at x equal to, say, 2, at x equals 2, so on this curve here, at x equals 2, let's say that's the point there, 2 what? 2, 5. At x equals 2, y equals 5. The gradient of the tangent, or the instantaneous rate of change, or however you want to put it, the gradient of the curve is, put 2 in there. So what are we saying? At x equals 2, what am I doing here? I put 2 in here, and I've got the gradient of the curve is 4. All right, that's just 2 by 2. So you put in your value of x there. So at x equals 0, what do we got? The gradient's equal to 0. Does that make sense? Look at that. X equals 0. Yeah, of course it does. Right, because my tangent would be horizontal at x equal to 0. So what we do is, by putting in any value for x here, we find out the gradient of the curve at that point, also known as the instantaneous rate of change at that point, also known as the derivative. So this is the derivative function, or the gradient function. Wow, there's stuff in there, isn't there? Okay, I'll leave it at that, and there's plenty for us to talk about next time we meet.